Okay, let's begin now. Thank you everyone for joining us today at the Polariton Chemistry webinar series. I'm Sindhana Paneer Sivajyoti and I'm a graduate student at UC San Diego. I'm honored to host today's speaker, Professor Päivi Törmä from Aalto University. Before we begin with the speaker's talk, I would like to share some information about the schedule and mechanics of the webinar. As you may know, the Polariton Chemistry webinar takes place every Wednesday at 9 a.m. PST. You need to register at this link for each webinar, and you can also follow us on social media for reminders. We've also set up a YouTube channel where we post the recordings of these webinars, so if you ever want to watch them again, you can watch them on YouTube. Now on to the mechanics of the webinar. During the talk, you can use the raise hand button to ask questions. Once you click on the raise hand button, I will interrupt the speaker and you can ask your question publicly. You can also use the chat to start discussions with other participants and to post written questions. Without further delay, let me introduce today's speaker. Päivi Törmä is a professor in the Department of Applied Physics at Aalto University. She received her PhD at the University of Helsinki, and she was a postdoctoral researcher at the University of Ulm and the University of Innsbruck. After that, she was a professor at the University of Jyväskylä and was a guest professor at ETH Zurich. She has received numerous awards and grants such as the European Young Investigator Award and the European Research Council Advanced Grant, and the Academy Professorship of the Academy of Finland. The research in her group ranges from theoretical quantum many-body physics to experimental nanophotonics. Her work has revealed a new connection between quantum geometry and superconductivity that explains why flat bands can carry supercurrent, essential in the search for superconductors that work at high temperatures. On the experimental side, they have worked on strong coupling of surface plasmon polariton modes and molecules, and they have succeeded in realizing the first plasmonic Bose-Einstein condensate. With that being said, I pass the microphone and screen to Professor Päivi Törmä. Professor.
Okay. So hello everybody, and thank you for the organizers for giving me this opportunity to present a talk. I have been following these webinars and I think this is really a great idea and very enjoyable. So I'm sharing my screen now, and I prefer to put the video off. So I hope everybody can see my screen now. So I will talk about Bose-Einstein condensation and thermalization of polaritons in plasmonic lattices. So let's start from basics. What is Bose-Einstein condensation? It's a rather complicated phenomenon that, however, arises from a very simple thing, quantum statistics. If you have classical or distinguishable particles, you can think about distributing two particles into two states, this blue and red, in these four ways. So they can be in different ones or in the same state. But now in quantum mechanics, if you have really indistinguishable particles, then for bosons, when they are in these different states, you must have only one state, which is a symmetric superposition. So this actually leads then to many things. For instance, that if you have a lot of bosons, the distribution looks like this. This is the Bose-Einstein distribution, and as you see, it may diverge. You get a condensate. And this phenomenon has been by now observed in many systems ranging from ultra-cold gases to semiconductor polaritons. It has been seen for photons, and it's also the basis of superconductivity. Now we have added one more system where you can see Bose-Einstein condensation. And this is a plasmonic lattice. I will today talk about mainly these two papers that are mentioned here. We first observed it in the weak coupling regime and then in the strong coupling. So I will start by telling what is a plasmonic lattice. Then I will somehow put our condensates on the map, because there are many types of condensate, even those which contain light. So it is important to understand where do we sit. And then I go through these two papers. First one was a BC in the weak coupling regime, and the second one is at the strong coupling. So there you will have polaritons. So I qualify for the seminar series. And in the end, I tell a little bit of our future plans. So plasmonic lattices. I have been interested in these systems for quite a while because they offer the possibility to do this type of bosonic many-body physics in a setting which is highly controllable. So you can make any kind of geometry that you want. For the lattice, we do this by E-beam. And then since these are plasmonic particles, they gather very high near fields around them, and this makes the light matter interaction strong, and that's why it's easy to get polaritons also in these systems, and everything works at room temperature. And what is really exciting is that the dynamics is in the sub-picosecond range, and there you start to play together with the vibrational dynamics of molecules, for instance. So we typically put molecules, dimolecules on top of these arrays, and then we see interesting things. So the basic modes that exist in such lattices are called surface lattice resonances. These SLR modes, I will talk a lot about this. They are formed in the following way. So first of all, individual metal nanoparticle has a localized plasmonic resonance. This means that it can act like a little dipole, and it radiates light, and it also has a strong near field nearby. And obviously, if you now arrange them about 1 lambda, but you can get constructive and destructive interference and new types of modes. And what we basically have is that this single nanoparticle mode hybridizes with a diffracted order that would exist in any periodic structure. And now we are interested in this in-plane diffracted order. So these two things hybridize. So in a spectra, you see here the broad single particle resonance, and here would be a very narrow diffracted order, and together they hybridize to bring up a funnel-shaped peak, which is our SLR mode. And these modes have also dispersion, because obviously you can also launch some in-plane momentum to the mode, and then you will have a different energy that matches that. So you get the dispersion. This K here is the in-plane momentum. And then you have different energies of the modes depending on K. And importantly, you get also band gap. So here you see a very nice band edge. And this we will need for lasing because it can give distributed feedback, and also for condensation because it's the ground state or the minimum where we condense. So we wanted to condense the excitations in these modes. And now, as I explained, these modes, they are largely light, which is just around the sample, but there are also the single particle resonances which contain electron oscillations in the metal. So it's a hybrid of light and electron plasma oscillation, this excitation that we are dealing with, and we want to condense them, put all of them to the ground state. The main problem was this. They have only about 100 femtosecond lifetime, and this is really, really fast if you want to get thermalization, which is important for condensation, and if you want to show and see what kind of dynamics there is. But we found ways to go around this obstacle and then really saw the condensation. But first, a little bit background. So this belongs to the context of plasmonic lasing in a broad sense, and there has been huge amount of work. I don't even try to put names here. I refer to, for instance, these review articles where you can learn about the lasing in nanosystems. But just to give some examples, here are a few names of groups where similar lattices have been used for lasing and condensation experiment. And we have done various things with these SLRs and nanoparticle lattices. We showed already quite some time ago that you can create polaritons in these systems. When, as I said, you put molecules on top of this array, we can put them either inside a polymer or in some kind of solution. And then we went to study lasing, various types of lasing, and we also can fabricate those particles from magnetic materials. Right, but let's go to the condensation. So here are some examples of things that you can condense. And you can do it, for instance, for photons, polaritons, or excitons. And the exciton part can be, for instance, inorganic semiconductor material or organic one. And depending on what you are looking at, the thermalization mechanism is different. So in condensation, what happens is that you give energy to the system at an energy that is higher than the ground state energy where you condense, and somehow you have to get rid of that energy and also get the particles to thermalize with each other. And in these systems, you use Coulomb interaction between the exciton parts of the polariton for that. While in organic polariton condensate, it's a different mechanism. It's you basically damp the energy to a vibrational quanta. So already in this seminar series, we heard a beautiful talk by Stefan Cohen about these organic polariton condensates. And there have been and will be in the future also talks about this inorganic semiconductor polariton condensates and so on. And then there have been experiments since 2010 basically about photon BECs. So these are not polaritons, they are just photons. But the thermalization mechanism is kind of related to the organic polariton condensates because they also use molecules that have a vibrational structure, and the energy is damped to the vibrations. So that's the thermalization mechanism, but the light matter interaction is at the weak coupling regime. Now our condensate, this first paper, is more or less here. So it's conceptually very similar to the photon BEC, but we are condensing a different quasi-particle. It's this SLR mode excitation, which also has the plasmonic part. And then in our second work, we are at the strong coupling. And now, interestingly, the thermalization mechanism, I would say it's something between these two. I will come to it. Then let me add one more dimension to this picture, the time scale. So here it's color coded, and you can see what is the typical range of dynamics. So in our first work, it was similar to organic polariton condensates. And in the new work, we have really in detailed manner shown that the dynamics is in the 100 or 200 femtosecond range. So it's basically the fastest condensation process that has been explicitly demonstrated. Okay, so now you understand more or less where our condensates are. So we can go to the actual results. And let's start from this weak coupling case. So no polaritons here. We have just the nanoparticle array, which hosts these SLR modes, which are mostly photons, but a bit of electron oscillation. And then on top of this, maybe here it's better pictured, we have a solution that contains dimolecules. Now the key in this observation was actually how we pumped the system. So we pump these dimolecules, so you put them to the excited state. But we do it only in one end of the array. What happens then is that they get, while they get excited, they give photons to these SLR modes, and those excitations propagate. And while they are propagating, they also slightly scatter out all the time. So we can monitor what happens along the propagation, and this gives us access to what happens in time, because you can turn, of course, distance into time when something is, has a velocity. Here are two things that you should learn to understand our results. So as said, these SLR modes have a band structure, and there is a definite band edge energy. This we can easily tune by changing the period of the array. Then we have the dimolecule with a large Stokes shift. And here we define an energy range where the absorption is negligible compared to any other rates in the system. And these two we have to change with each other. Of course, it's this one that we tune up and down. So here you can see how the thermalization works in our case. We pump the molecules, but only in one end of the array, so they go to the excited state. And they give photons then to the system, and the excitations propagate. But when you excite before emission, there is some vibrational relaxation, so you actually emit a lower energy photon to this dispersion of the SLR mode. And this then happens many times when excitations propagate. They excite here molecules, and those again lose some energy to vibrations and so on. So you get the redshift. So this mechanism has been used before. And we hope that this could work also in our case. So let's see whether it happens. So here is a cartoon of what is going on. And just to see the thermalization, we can put now the band edge at the place that is above this energy where absorption vanishes. So after exciting the molecules, they can emit photons, and those or these SLR modes, those get absorbed. And then before further emission, there is some relaxation, and you go to the band edge, but there is still some absorption left. So you can go to the lower branch. And this is actually what we see then in the experiment. So here is spectra that we record, spatially resolved, like along this propagation. So this is the array, and this really is the array coordinate here. So we see emission here at high energy where we pump, then redshifting, reaching this band edge energy, it's here, but then it jumps over here, and here it more or less then stops. We can integrate now the population along this band edge. It's this blue thing, so it grows a little bit, but then goes down. And the redshifting part means all the other light. So mostly it stays somewhere else. So we see the thermalization process here, but there are no condensate. To actually get the condensate, we have to match this band edge and the point where absorption stops. So now it's the same emission, absorption, vibrational relaxation, emission. And now, since there is no absorption left, you will get a bosonic stimulation to the ground state, and the condensate forms. And that's exactly what we see. So here, thermalization, and then you see a very prominent feature at the band edge energy. You can integrate again this band edge, and you see how it grows, and it's really fed by this thermalizing part. Now, in this type of all of these polariton and photon and whatever condensates. Yes.
We have a question.
Okay.
Yeah. Well.
So, sorry, Päivi. For those of us who are not as familiar with condensates as you, can you just clarify to us the signatures that make these different from lasing? So like what would be, so I guess you're going to be looking for a Bose-Einstein distribution or something that tells you that it's thermalized, but yeah.
Yeah, so I will come to that, but it's basically the Bose-Einstein distribution is a feature where you can see it from experiment. And then you also somehow has to show that this thermalization happens. And maybe I go to my next slide, because here we can, this was essential that we could monitor this redshift process and then the condensate forming. And this is non-trivial, I will say soon, but exactly this.
Let me just ask you one question, but then the energy gap between the bottom of the band of the SLR and the top of the lower band, what is that energy gap need to be so that this happens efficiently and there is no relaxation to the bottom?
Well, in our case, it's couple of milli-electron volts, but it yeah, it doesn't need to be very large. It's just that somehow you have to then get a condensate peak that is narrow compared to the band gap. Then you can have it.
Okay.
And also having you know, narrow peak, it also depends on how much you pump.
Sure. Okay.
Yeah.
Thank you.
Yeah. Okay, but to this, your important question, what is the difference to lasing? And this is really central in all these photonic or luminous condensates that have a photon part, because in these systems you also see lasing. So what is the difference? And we can show here one difference. So conceptually now we put this band edge energy to a position where there is absolutely no absorption, like it's completely zero. And what we see here, we see immediately lasing. So we don't have this redshifting part here. This thermalization doesn't happen. Instead, we start to lace, and the system starts to lace already in the beginning of this array. You see it on the integrated population at the band. It's immediately one. So these pictures were one signature making a difference to this BC, where you clearly see the thermalization and the condensate forms here, and then the lasing where you see only population at the band edge and nowhere else. And then there are other things like the distribution. And I will show it here. So we now take a spectra from this area where the condensate has formed. And we can see.
We have one more question.
Yep.
Joel, go ahead.
Okay, sorry to bother you, Päivi, but just experimentally, can you just remind the audience? Okay, so in your lasing experiment, what was the main? Okay, so you say that the lasing occurs also at the band edge, but experimentally, what do you change compared to the BEC experiment? Like,
yeah,
what is the different
it was
experimental
this
condition?
thing. This position of the energy, the band edge, compared to the position where absorption is small. So here they are kind of matched, and then in the lasing, we put this band gap energy here. So here you have still some emission, but absolutely no absorption left. So you have actually a lot of effective gain to the band edge, and therefore it starts immediately lasing.
Okay, thank you.
Yeah. So one can really play in this system, get both phenomenal lasing and BC just by changing the parameters. And then here we saw that as a function of pump fluence, we see this nonlinear building of the peak at the band edge. And indeed, it follows nicely the Bose-Einstein distribution at room temperature. Later I will show better distributions also from our new experiments. And another thing kind of distinguishing between lasing and BEC and so on is to compare the theory, and we have done it within the Kirton-Keeling model. So the behavior is very similar, and also the nonlinear behavior is very similar. But now maybe if you are observant, you see that here we have time instead of this spatial coordinate. So this is really spatially resolved spectrum, while here is time in our simulation. There is no spatial dependence in the simulation, and this is somehow our idea that we can turn the distance into time, that since things are propagating in the array and we monitor them along the propagation, and from the dispersion we know the group velocity, then we can get the connection between time and distance via the group velocity. And therefore the simulation looks the same in time. And from here you can see that everything happens within 1 picosecond about. So in this kind of experiment, we get access to seeing what is happening in the sub-picosecond scale, and this is actually highly non-trivial. Okay, so there is a lot more characterization in our paper. You can look if you want.
Professor, we have a few questions.
Mm-hmm.
Matt, go ahead.
Hi, do you hear me?
Yes.
Okay, I was wondering, what's the possibility of doing these weak coupling BEC experiments with microcavities?
Yeah, the BEC of photons have been done by Martin Weitz. He used some quite high quality cavities in microcavities. Yeah, why not? I think there is no conceptual difficulty, at least. For us, this lattice is nice because it's kind of open from the top. So we can monitor this propagation and everything. We see kind of what happens. So that's one nice advantage here. And it's also really easy to tune the band edge energy very accurately. So these are for us, the advantages of this type of system, but I don't see in principle difficulty doing it in the microcavities.
Oh, okay, thank you.
And we have one more question. Randall, go ahead.
Yeah, thank you. I have a question about the previous slide. So the transfer or the relaxation in the molecule as a characteristic timescale of picoseconds, that's what you have here. I thought that, at least for a single gold nanorod, the longitudinal surface plasmon has an excited state lifetime that's way sub-picosecond, maybe like 100 femtoseconds or something like that. If that's true for the SLR, then I don't see how you accumulate energy. What's the relaxation rate? Why are you able to accumulate population at the bottom of that upper band?
Yeah, so that's a really good question, and there are kind of two things that contribute here. One is that this relaxation mechanism, or this redshift here, it's a stimulated process. So we have a lot of photons, and in the next work I will show really explicitly that it's stimulated. So you should not think about the relaxation times of single isolated molecules. So the photons that are already in the system, they stimulate emission faster than it would happen for single molecule. And another thing is that we start with huge numbers of molecules, and of course, since the SLR lifetimes are short and so on, by the way, the SLR lifetime is about 10 or 100 times more than the single nanoparticle.
Okay, that's what I was missing.
Yeah, but still, we lose a lot of photons. So this is like in ultra-cold gases, some kind of evaporative cooling that we lose a lot of particles. So actually, the signal here is rather weak.
Why is the SLR lifetime so much longer than an isolated plasmon?
Because you hybridize the plasmon at the single nanoparticle with photons, and the photons have like a high life.
Okay, thank you.
Right. Yeah. Okay, but let's then go to strong coupling and see how this thing works with polaritons. So in this work, we first of all we have polaritons. So here is the dispersion without the molecules. And then when we put the dye molecules on top, and then we see, so this would be the dye molecule absorption energy, and this would be the dispersion. So they repel each other. You get this bending and this shift, and this tells that you are in the strong coupling regime. And we also, in this experiment, we pump all over the sample. So we don't use this propagation trick. We still see nice stuff. And moreover, we also vary the pump pulse duration in a controlled way, and this gives a lot of information. So let's see what happens, and actually something quite different happens. We see a double threshold behavior here. So this is the pump fluence and output intensity. We see one threshold, a plateau, and another one. And the first one we associate with what we would say is a usual lasing in these systems, polariton lasing in this case. The real space image looks like this. So this is now just XY direction of the sample. We basically see light all over the place. I mean, this is some imperfection. It should be bright all over. And then we can take a spatially resolved spectrum. So this is energy. This is one of the array axes. And you see that all over the array, you have basically light at one frequency. So that's this lasing. Here, then we see this BC again. So now, since we pump on the top of the sample, we have actually 10 to the power 5 more photons. So we see everything much better. So we can see this Maxwell-Boltzmann tail, that is the fingerprint of a BC, very prominently over more than 1 order of magnitude. So this is in log scale. Here is the BC peak, and this is the Maxwell-Boltzmann tail. So this is a really nice BC happening here. Spatially, it seems to be more like centered in this array, in contrast to lasing. And the lasing regime and the BC regime are also different, radically different, in the sense that one is coherent in one dimension, the lasing one, and the BC is 2D coherent. So we made a Michelson experiment where you can probe the coherence in both directions, and then for the lasing pump fluence, which is here, we see coherence mostly in the Y direction. And now I didn't tell why this Y. I mean, the pump polarization prefers one direction over the other. So if your pump polarization is like this, then you preferably build up coherence in this direction. You kind of excite the SLR modes that propagate this way when you have this pump polarization. Otherwise, the sample is quite symmetric. And then when we have higher pump fluence and we reach the BC, this regime, then we see the coherence building up in both directions, even when initially we pump only in one. So they are really different from each other in this respect. But then there was also this interesting plateau area where definitely we don't have any lasing or condensation, because you see the line spectrum here, there is no peak whatsoever. but the spatially resolved and the real space picture and spatially resolved spectrum look very interesting. So here you see the redshift process quite clearly, that we start from higher energies and then emission goes to lower energies. And this seems to happen as you go along sample. Moreover, you have here this kind of low intensity areas and more stuff in the middle. And then there are these fringes. Well, these fringes, they simply come from the K vector that you have for each energy. So we have this SLR dispersion so that each energy has a specific K, and the fringe contrast here is not contrast, the period corresponds to this K vector. So it's like two propagating wave fronts meeting and they interfere. This we understood, but why these other features? Why these low density areas and so on? And we thought that maybe we understand if we try samples of different
Professor,
sizes. Yes,
we have one question. Go ahead, Andrew.
Yeah, I have a question. Thank you for a very interesting talk. You are saying, do I understand correctly, that you are saying that at some moment you have a lasing, and then when you increase pump further, you lost the lasing?
Yeah, yes.
Could you comment this point a little bit more? Thank you very much.
Yes, I'm kind of comment. I mean, what happens here is that another process starts. So there are three competing processes. It's this lasing, and then here the BEC, and here what we call it is we call it a stimulated thermalization, and I will explain now what kind of process it is, because obviously it's not the lasing process here. So, but how we got to the our explanation is like this. We made now lattices of different sizes. So here a small lattice, medium, and large. And then we do the experiment in each. And at first glance, we thought, oh, this just brings more trouble because they all look radically different. So here you have bright area in the middle. In the small sample, it's empty in the middle. And also these redshift features look very different. But then we realized that if we actually measure this low intensity area here, and here, if we measure it from this point up to this point, it's always the same. It's always, in this case, 25 microns. So what is this? And then we came up with the explanation that there is a stimulated pulse formation process going on. So in general, if you form any kind of pulses by stimulated emission, you can describe it by simple rate equations in this way, that in time you have first a pump pulse, and this creates population inversion in the gain medium in your molecules, up to some point when the population starts to go down and the output pulse forms. Now this distance from maximum population inversion to the output pulse formation is called the pulse build-up time, and it depends only on the pump fluence, this one. So now if we think that in our sample at each position you start this pulse build-up and you put they will the excitations will be in modes that propagate. So at the same time as you build the pulse, it also propagates. So you get this kind, then it goes down, this kind of Gaussian. And you have both these things going to both directions, but you don't start anything from outside the sample. Therefore, you have less intensity at the edges. And we can plug the numbers in and do the simulation. And indeed, in the simulation, this gives the same empty areas or empty or low intensity areas as we observe. And we can test this by having different sizes of arrays and varying the bump fluence, because this should change the this length of this low intensity area, and indeed it does. All the data falls on the same line, which is the one that we expect. So this is what happens. There is a stimulated pulse formation process, and at the same time that these pulses are formed, you also have the redshift. So here, the energy of the emitted light comes down. And in the small sample, the pulse formation starts only here, and then you have the redshift. So you don't have a counter-propagating wavefront coming. That's why you don't see the interference here, but you see it here. So we have shown that this thermalization really happens in ultra-fast timescale. We get the timescale from this analysis, and it's about 100 to 200 femtoseconds. And then we tested this further by varying the pulse duration, and it was 50 femtoseconds before, and now with 500 femtoseconds, we only see this lasing. So one threshold and then lasing, lasing, lasing. So this process doesn't start if the pulse is too long, even if it has the same integrated energy. So this tells that the dynamics is extremely fast, and also that you need very high peak, momentary energy in the pulse to launch this stimulated thermalization process. So this now would require beyond the state-of-the-art theory to explain, because ideally you would have molecules with a vibrational structure, and then they have to be in the strong coupling regime with the cavity modes, and you need many cavity modes to describe thermalization. So this is something that nobody can really fully do at the moment, but we made this kind of a toy model to illustrate it. So this has only one molecule with one vibrational state and several cavity modes. And if you now simulate fully coherent dynamics, so this here is time, here is energy, and these different energies are different cavity modes, and here the different colors are different cavity modes. So you can see that the population goes mostly to this mode. It's the green one here. This is the one where the vibrational energy kind of, if you lose one vibrational quanta, you end up here. So it's kind of favored, but in a fully coherent process, you just go back, you oscillate. Then if you add vibrational losses, you can get really some redshift and thermalization to these lower energies. Again, here, this green one is the vibrational matching energy. This kind of is high here. And then if we add both vibrational and cavity losses, we see very clearly that it likes to relax to certain lower energy. So this hints kind of qualitatively that something like this is happening, but we cannot yet fully simulate what is going on. There is an advance by Jonathan Keeling's group and us, where we have made a strong coupling multimode theory, but this still is like spatially uniform and cannot handle so many degrees of freedom that we actually need. But it's a step forward. But this is something that well, we would be happy to get some theory input somewhere. Okay, and finally, very briefly, some other stuff that we have done and future directions.
Professor,
yes?
We have one question.
Mm-hmm.
Yes, go ahead.
Hi, thank you. So actually, I have two questions. The first one is about the dark mode. It is a type of optical bound state in the continuum, because you mentioned you use dark mode to show lasing. Have you ever tried to use the dark mode to study condensation? It seems like you always use a bright mode for the condensation.
Yes,
So
yes. Yeah. So far, Yeah, these are bright modes because we see emission from all over the sample, and indeed in our previous lasing paper we also saw the dark mode. We have been thinking about this, but so far we have got easier the BEC in these bright modes. It's also that it's a bit harder to analyze the dark mode because it mainly comes out from the edges of the sample. But it's a very interesting idea, and I'm really curious to try it in the future.
Okay. Yeah, so my second question is about the optimal energy of the band gap for realizing strong coupling, for realizing condensation in the strongly coupled system.
Yeah.
What's the physical origin for the optimal energy? Because for the plasmonic condensation, you mentioned the epsilon, the epsilon energy. But for the strongly coupled system, how do you find out the optimal energy for the band gap, for the band edge?
Yeah, actually here we did not optimize it very much. We just tried, because it's so easy to try different band edge energies. We tried, and for this one, we see it very nicely.
Yeah.
So this is not even the one, the same optimal condition that we had in the decoupling paper. This just works, and yeah. We don't know exactly why. Maybe it's the gain conditions are somehow optimal.
So you mean when you vary the band edge energy a little bit, you can also get this kind of behavior, like the double threshold behavior.
Yeah.
Okay.
Yeah.
I see.
Yeah.
I see.
Yeah.
Okay. Yeah. Thank you.
Mm-hmm. All right. So. Then about slightly different topics. So we have done many studies on lasing and BEC, and also others have done, and they have all been at the gamma point. So this means a normal incidence laser beam and a standing wave in the system, so zero K vector. But of course, you could have interesting high symmetry points also elsewhere in the Brillouin zone. For instance, if you have honeycomb lattice, these K points are interesting. So here you have a dispersion of honeycomb lattice measured. Here's the gamma point, here is a K point. And we were interested, can we see lasing there as well? Because then later we can maybe open some gaps there and make the system topological and so on. And the answer is yes, we can see lasing. And now, since it's at the finite K, this means that it's at the finite angle. So we actually get 6 beams to different of normal angles. And yeah, so this is really the honeycomb geometry, but now you can immediately forget about all tight binding model knowledge of honeycomb systems that you know, because these lattices are very far from tight binding. All the particles are radiatively coupled. So we didn't get much hint of what to expect based on any tight binding model, but there is still the symmetry. And this seems to be a very useful tool in analyzing these nanoparticle lattices. So based on the symmetry, you can immediately conclude that in the K point, you can have these irreps, a doublet, which is degenerate, and 2 singlets. And here are how the dipoles look at nanoparticles, and this is how polarization looks at K point. Sorry, in the K space. And then now we have our lasing experiment, 6 laser beams coming. This is now in K space. And we can measure the polarization at each of these beams, and they are like this. Then we can immediately deduce that, okay, it's the singlet one that is lasing in our case. So this will be very useful in the future when we want to, for instance, break the degeneracy of this doublet and see how it becomes topological and so on. We can see from polarization what is going on and which mode is lasing. And this I more or less said what do we want to do on that line of research in the future. And in the BEC side, this kind of more detailed theory would be wonderful. And also we want to do things like study the spatial coherence, polarization dependence, and so on of this BEC. Finally, the important people on this work. So have been postdoc Tommi Hakala. He's now a professor at University of Eastern Finland. And then PhD students Antti Moilanen and Aaro Väkeväinen. Antti is here. He has done both experiments and theory for the BEC. And Aaro has done experiment, and he's already finished and is working in the industry. Then we have other people who have also contributed greatly. So postdoc Kostas Daskalakis and former PhD Heikki Rekola for the experiments, Aleksi Julku and Marek Nekada for theory, and Rui Guo, especially on the K-point lacing, and Jani-Petri Martikainen, he's lecturer for the theory part. So thank you very much.
Okay, so we have reached the final part of the webinar. So do we have any questions? Okay, we have one question. Wei, go ahead.
Yeah, thank you, Päivi. So you probably mentioned it. So how did you exactly overcome that short lifetime of the plasma in the strong coupling case to let it condensate?
Yeah, so here in this one, oops, everything happens extremely fast. So all this stimulated thermalization process and pulse formation, it's just a few hundreds of femtoseconds. So well below picosecond. So that's one reason that we are actually around the lifetimes of these SLR modes. And the second reason, we pump hard, so there is gain.
Okay, thank you.
We have one more question. So Xiao.
Yes. So could you please explain why the BEC threshold is higher than the lasing threshold in your sample?
That's a good question. We don't know actually. Yeah, this is something that we would like to understand. So obviously this BEC needs this stimulated thermalization process to start. So in one way you can wave hands that it's more complicated process, but honestly we don't know why this lasing wins, but it just happens to win. Like it has a lower threshold, and then later, yes. But this is in general known that if you have several different type of processes in a pump system, you can get you get for low pumping, you get the one that has lowest threshold, and then, for instance, in lasing later, another mode which has a higher I mean that it's kind of more non-linear, slope efficiency. Yes, then that one takes over. So that's known in general that these competing processes exist. But why particularly here first lasing then BC, we don't know.
We have a few more questions. So, Joel?
Hi, Päivi. This was a very nice talk. I wanted to ask you something that I find confusing in all this business of condensation. So first of all, condensation happens, you definitely need population inversion, right? For all of this, just like in lasers, right? That's my first very simple question.
Well, in principle, for condensation, you don't need population inversion, and that's exactly the difference. So for instance, for Polariton condensates in semiconductors, it has been shown, at least by theory, that you don't need. And indeed, the thresholds can be lower. In our case, we don't know whether we have population inversion, so I wouldn't say anything definite here, but conceptually, it doesn't need.
Even if you didn't have population inversion, something that I find very strange, something that I don't understand is, in these molecular polariton systems, as people ramp up the fluence, they notice a reduction in the Rabi splitting because of the bleach of the ground state. So then what I don't understand is, when you pump and pump harder and harder, then eventually the lower polariton and the upper polariton start merging with each other. So how come you don't see that and you see condensation instead? Is there a simple way to
well, we see this blue shift also in our data, but the polaritons are not completely gone here. So in the paper you can go and see the blue shift.
So are you saying that the upper and lower polaritons are still there, even though the lower polariton is going up in energy?
Yes, they are still there.
And is the upper polariton also going down in energy or going up in energy?
We can see the Rabi splitting to you know, in a way we don't even observe the upper polariton because this is the lower one, but we can see it developing in such a way that we know that there is this depletion of the ground state and this reduction of Rabi splitting.
Thank you.
Professor, we have one more question. Okay. Fine, go ahead.
Okay. I don't hear anything.
Yeah, even I don't. I think you're muted.
Maybe
yeah.
The microphone muted?
Yeah, I think so. Oh, yeah.
Hi.
Hi.
You hear me now?
Yes.
Yes.
Okay. So on your multimode part, so are those normal modes?
Sorry?
So can you go to your multimode theory part?
This one?
Oh yeah,
no?
Yes.
Yep.
Oh yes, this one. So so are those modes normal modes or?
So in this model, we had, yeah, these are just general cavity modes of a simple cavity. So they don't correspond to our SLR modes. So this is a toy model in that sense.
Okay.
So they are basically just different energies where the light can go. They don't even have like spatial structure or something. It's really just very simple toy model.
Okay. So did you implement this model in your lattice structure or?
No, we have not done it. It would be much more complicated.
Okay. Okay. Thank you.
Okay. So I think we have come to the end of this.
Okay, so I want to say thank you for everybody for listening, and bye-bye to everybody.
Okay,
or
so
you have something still.
Yeah, I just have to basically talk about the next speaker. So let me share screen. Okay.
Should I stop sharing mine?
Yeah, I think so. Thank you, Professor Päivi Törmä, for the wonderful talk. We sincerely appreciate you being a part of this webinar series. Today, we hosted about 115 attendees, and we're hoping to see more participation from the community. It's great to see so many people. Just one quick announcement. Next week, we will have Professor Nipa Mehta as our next speaker. Remember to register at the link. And finally, we would like to thank all the participants Thank you.
Should I answer now this?
Oh, the Q&A. Yeah, you can answer one last question from the Q&A.
Yeah.
Hi, Professor. Yeah, so I'm wondering, can you explain more about the dark mode? And so is this a type of optical bound state in the continuum?
Yeah, it's the same same thing. It's just two different names to it. And in our case, the dark mode is born in such a way that these nanoparticles can host not only dipoles, but also quadrupole oscillations.
I see.
And then this doesn't couple to the far field. So
I see. So based on different, lattice structure, sometimes the dark mode is above the bad edge. Sometimes the dark mode below, right? So can you comment on that, or how can we design, for?
Yeah. So this can be tuned by changing the size of the nanoparticle. So I have, I think it's in the, I have a physical review letters paper from 2014 where in the supplementary we vary it. So we have rod-like particles, and then we vary the length of the rod, and we can change from having this bound state in or continuum or dark mode either above or below. So that can be certainly done.
Okay, I see. Thank you. Thank you so much.
Okay, I think we have come to the end of the webinar series. Thank you everyone for participating, and thank you, Professor Päivi Törmä.
Yeah, okay, thank you. Bye-bye.